we go. All right, you're on the air, folks. So, chapter 1. And I'm going to start off with just some stuff that you're really supposed to know already. But if you haven't had IPS or chemistry, then this might be new for you. But there is a nice figure. It's figure 1.1 on page 4. And I'm just going to redraw it and then talk about it a little bit. It's basically the classification of matter. And this might seem really basic, and that's true, but there's some key kind of ideas in here that if you don't get will be a source of confusion for you for a long time. So first of all, we divide matter into 2 groups. One is pure substances. Some textbooks just say substances instead of pure substances. And then the other is mixtures. Now what you're going to see as we continue to break this down is that as with any classification system, there are gray areas, there are kind of arbitrary divisions, and things are not always clear. Think about the duckbill platypus, for example. Not everything. Think about what's the difference between a shrub and a tree, for example. So there's not always clear distinction between groups in any classification system, and that's true here as well. But the pure substances part is fairly straightforward. That is divided into 2 groups, which are elements and compounds. Now this, in my mind anyway, the best way to understand this whole scheme is right here. Start with these and say that elements and compounds, if you understand what those 2 are, those are what we call pure substances, and nothing else is a pure substance. So if it's not an element or a compound, it's a mixture. So that part is pretty straightforward, I think. Compound means you have more than one element, and they are chemically combined. So they have been joined through a chemical reaction. So we'll say more than one element chemically combined. And then I'm going to add on here, even though technically it's not an absolute rule, they have constant proportions of their constituent elements. So in other words, it's H2O, not H3O or H4O. It's H2O. So it's a constant proportion, and that leads to a constant percentage. So if you were to weigh them, they're always the same percentage. Table salt is always the same percentage. Salt is around 35 or something like that. Always the same percentage sodium, same percentage chlorine. Now, on the mixture side, things get a little bit more tricky. We have 2 kinds of mixtures. One is called heterogeneous. I should put the O up here, sorry. Heterogeneous, and the other is called homogeneous. Homogeneous mixtures are also known as solutions. Now the easiest way to deal with this side of the diagram, I think, is just this right here. Just realize that, okay, if you're not an element or a compound, you're a mixture. And if you're a solution, then you're a homogeneous mixture. Everything else goes into the heterogeneous category. So let me give you an example. This is a heterogeneous mixture. It's a piece of granitic gneiss. It's fairly common rock in the eastern part of this state. And I can see, if I look, I can see some dark colored minerals, some light colored minerals. I can see some quartz in there, maybe some what looks to be some mica. The fact that I can see the different constituents of this as they are mixed together means that it is heterogeneous. So we're going to make a fuzzy distinction between these two that says on this side we can actually see with our eyes, with the naked eye, the separate constituents. And in the solution, we cannot. So look at this one right here. This is a solution of nickel nitrate, and it just looks like green water. So I see a color, which comes from the nickel, but I cannot see the individual particles of nickel or nitrate. I can't see the water molecules. So to me, this looks like it's all the same everywhere. It's homogeneous. Yes?
Now, if it's saturated, does that qualify as heterogeneous?
If there were crystals in the bottom, that would be heterogeneous because I could see the crystals. But right now, it's homogeneous. Yes?
And how is it saturated? Is it now super saturated?
It's not saturated right now. I mean, I don't think it. No, it's probably not saturated. Saturated would just mean that I can't dissolve any more stuff. Yeah. Now, homogeneous solutions can take. They can be solutions. Remember, can be liquid, gas, or solid. And that's important to keep in mind because we normally think about solutions as being liquids, but air is a solution. And alloys like brass are solutions where you have two metals that are mixed with each other homogeneously. So solutions don't have to be liquids. Now the reason I put this fuzzy line here is because imagine this, take this rock and make those crystals smaller, 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 and smaller. At some point, you could imagine them getting so fine that this looks like just a uniform gray mass. Or think about it like this. Shrink yourself down to the size of a molecule, and this is no longer homogeneous. There will be little areas in here where there's clusters of nickel, and the concentration is actually not uniform. It's uniform from our scale, at our scale, but not at the scale of a molecule. So what we're doing here is we're saying that at kind of a macro scale, it's homogeneous or heterogeneous. And one quick way that you can tell between a solution, a liquid solution, and a heterogeneous mixture would be to shine a light through it, and like a laser. You shine a laser through it. If you can see the laser beam, that means there are macro-sized particles in there that the light is bouncing off of. And then you would call that a suspension rather than a solution. Questions about those points of classification? One of the kind of finer points of this is that mixtures can be separated physically. Whereas compounds must be separated by chemical means. Of course, that begs the question of what a chemical mean is. Through a chemical reaction. It's a little bit circular because if we say that it has to be separated through a chemical reaction, well, one of our criteria for a compound was that it was chemically combined. So you it's a little bit circular, but that's, like I said, all classification systems are a little bit messy. People invented this thing. Really, this goes back, this kind of way of thinking about things goes all the way back to Antoine Lavoisier. He was kind of the first one to really clarify the difference between compounds and elements and solutions. Well, it was through his work that we started to clarify that anyway. And then also in the time of John Dalton, I guess, is where it was totally settled. Early 1800s. So what do we mean by physically? This could be filtration, could be distillation, it's interesting that one of the controversies in the time of John Dalton was, and one of the reasons it was so hard for people to see kind of the truth of atoms and that atoms were combining to make compounds was because at the time, up until John Dalton, everybody saw solutions, everybody saw solutions as the same as compounds. And it was because their theory of chemistry at the time was called affinity theory. And so they talked about how some elements had an affinity for other elements. And so they really couldn't see any difference from the dissolving process and the chemical reaction because they explained them in the same way. They said that the nickel nitrate has an affinity for the water, so it dissolves into the water. And anything that reacts chemically, those two constituents have an affinity for each other. So they didn't see a difference, and because of that, the fact that solutions can have variable compositions kept them from seeing the idea of constant proportions, which was necessary to come up with the atomic theory, which was that atoms combine in simple whole number ratios. So it wasn't until John Dalton came along and basically just assumed that you would have these small whole number proportions and that they would be constant that people were eventually able to give this up. The idea, and once you saw these as separate things, solutions and compounds, it kind of opened a whole new way of looking at what was going on. But I think we'll get into that a little bit more later, so we'll save that. Okay, so the next section in your book is talking about measurement. And I'm just what I'm trying to do is just kind of hit some highlights as we go through this and what I think are really the main points here. But again, don't take this as a substitute for reading your text. Yes?
You say that mixtures can be separated physically. Do you think that it can be separated chemically also?
Well, technically no, because they're not chemical compounds. So when
They must be separated physically?
yes. So when I say chemically here, what I'm talking about is you've got to actually have a chemical reaction that takes place to separate a compound. But like I said, it's a little bit circular because if you do separate a compound, then by definition you're doing a chemical reaction because you're changing the substance into another substance. So it's a little weird. Yes?
The book also talks about chromatography, which is another separate.
Okay, right, yep. So we can put chromatography down here. Yep.
What is that?
Chromatography is something you'll get a chance to do in a few weeks. It is, the simplest type is called paper chromatography. So you take a piece of paper and you put a classic example. I think some of the biology teachers do this with ink. So you take like a magic marker that has maybe like a Sharpie, and you put a dot of the Sharpie on here, and it turns out that it's not pure black ink. It actually has component colors. This is a number of dyes that are mixed together. You put the end of this in something like ethanol, an organic solvent, and as this solvent starts to wick up through the paper, it carries with it the dyes. But the dyes are different sizes, and they have different, so they travel with different speeds through the paper. And so you end up getting like different colors at different locations. So it might separate them out, something like that. As the ethanol is traveling up, it pulls them at different speeds with itself. They have different, it kind of has to do with the ratio of their attraction to the paper versus their attraction to the ethanol. Or the size. I'm not sure. It could be both. There's both factors involved. Yes?
So just chromatography and deal more on a molecular level rather than
Yeah, it separates them at a molecular level. Sure. Yeah, so does distillation. And filtration could do that too, depending how fine your filter is. Distillation is the trickiest one because you're heating it, right? So you're having to put energy into it to get it to happen, yet it's still considered a physical process. And the way to remember that, I think, is just, if you can remember that a solution is a mixture, then you can remember that distillation is a physical process. Because distillation is how you separate a solute from its solvent. You can remember that a solution is not a compound. And like I said, that dates back to 1803 or something like that. Really, what are these? This is all just a model of the world, right? It's a way of looking at the world. And so really what chemistry is about is learning a new way to look at the world. Possibly a way that you don't really want to use, but you will be, and you'll become very good at it by the end of this course. You will look at things in a different way. All right, for measurement, I just want to point out a couple things, and that the first is that really all measurements are relative. And what I mean by that is there's no such thing as like an absolute unit when you think about it that has like some kind of independent existence. If I am measuring something with a meter stick, I mean, what is a meter? Well, it turns out it's some fraction of the distance that light can travel in a certain time, all right? It used to be a certain, like, 1/10,000th of the half the distance around the Earth or something like that, I forget. So but even those things were arbitrary. So even if you say that it's going to be 1/10,000th of the distance between the poles or something like that, you're still making an arbitrary decision as to what this is. And that's true about anything. When we measure mass, if it's grams or kilograms, it's all relative to some chunk of metal that's under glass somewhere in France. So it's kind of, there's an arbitrariness to it. But the purpose of it, of course, is that we make it standardized. That's when it becomes useful, right? So we make this, we start off with this kind of arbitrary thing, like we're going to say that this length is called a meter. But it becomes very helpful because we standardize it. And everybody uses the same standard. And now we can compare notes. But the reason I mention this is because you'll hear terms like absolute mass versus relative mass, for example. And there's really no, that distinction is a little bit artificial because really all masses are relative. They're just relative to some standard. That's where the difference comes in. So let's talk just a little bit about each type of measurement we can make. We've got length, and of course we'll be using a meter for this. I put up on Moodle site, I think it says the SI system. Yeah, so let's see. We click on this. This is just, I think, hopefully a helpful little summary of the SI system for those of you who might not be as familiar with it. Because, like I said, you're gonna have to memorize all the SI units. And you'll have to be able to do all the conversions between them. This thing always gives me a hard time opening. There we go. Okay. So here we are. We've got the SI units for each of these things: length, mass, temperature, time, and so on. And then I have a whole bunch of the prefixes. Now, these are prefixes that you should know. So you should know these prefixes and what they mean. Here I've got them in form of decimal notation and then also exponential. And the cool thing about the SI system, of course, is that you can build any unit you want. If you know the prefixes, you know the base unit, you build any unit you want. So you just take this, and if I can have a centigram, and I know that that's just 10 to the minus 2 grams, or 0.01 grams. I can have a gigagram, and I know that that's 10 to the 9th grams. So pretty straightforward. It's just a matter of memorizing these things. The nice thing is once you get past milli, it goes every 3 powers of 10, right, as I'm sure you know. And then it's funny because I need to extend this because since I made this, which was like 10 years ago, giga is really not that big anymore. So we have to go up to things like tera and peta, right? I mean, in computing now, they're talking about like petaflops and stuff for processing speeds. We'll, let me see. I don't think I have on the other side here, but, oh, here we go. This is the full list, folks. Actually, it's not the full list. I think, didn't they, am I wrong, or did they just say that Hella was going to be up above at 10 to the 27? Yeah, so I need to update this list too. But this is this is the full list. You don't have to know all these. The ones on the front are the ones that you should memorize. Although, as I said, things like tera and peta are becoming much more common these days. And yeah, anything greater. Now, this is a little out of date, this little joke here. I'm going to have to change this because we have one now officially for 10 to the 27. It's Hella. It's not. So anyway, this is just some practice you can do, but this is for your information. So we'll be using the meter, and in this class, we will see a lot of the centimeter. In particular, we'll see a lot of the cubic centimeter, but let's not go there yet because that is a volume. When we talk about volume, volume is not a fundamental unit because it is made of length cubed, right? And so in terms of SI units, sometimes we'll be using units like centimeters cubed and meters cubed for volume. How about this one? Liters cubed. We use that, you think? No. Liters cubed would be meaningless. Okay, you can't have it. Liters are cubic. All right, they already have 3 dimensions, so don't go cubing it again. Now you're like in, I don't know, hyperspace or something like that. All right, so then we got, after volume, we talk about masses, and this will be our most common unit that we'll use in here. We'll be using grams very heavily, although you might see milligrams. In chemistry, a lot of times you'll end up using smaller units also, like micrograms and even nanograms. Yes?
How does the microgram differ?
Good question. So because we have to be able to distinguish between M in milli and micro, this is the Greek letter M, so this is mu. And that's micro. So it's a Greek U. Or the Greek M, sorry. It looks like a U with a tail on the front. And then we have nano and so on. With length, by the way, if you want to talk about on the scale of an atom, you're going down to nanometers and picometers. That's atomic scales. There's another unit that's called the angstrom unit, which is 10 to the minus 10th meters. Has this symbol here. It's called an angstrom unit. It was devised pretty much just for atoms and molecules. So we're in that range because that's 10 to the 9th, 10 to the negative 9th, 10 to the negative 12th. lastly, temperature. Of course, we could talk about time also, but we can only measure to the nearest second in here. We don't have capability to go to like picoseconds. Temperature, if you want to look at degrees Fahrenheit, the equation is 1.8 times the degrees C plus 32, and degrees C is going to be degrees Fahrenheit minus 32 divided by 1.8. And then Kelvin, of course, Kelvin temperature is degrees C plus 273.15. These are given to you on the tests. So if you do need to do any conversions, we shouldn't even be using Fahrenheit in here. Of course, I grew up using Fahrenheit, so it's tough for me to think in terms of Celsius, but I like to think about kind of the key points, right? When you look at the Celsius scale versus Fahrenheit, it's nice to keep in mind a few key points. Of course, 100, boiling point of water, is 212. 0 is freezing, and then we've got a couple points in here. 37 is body temperature, right? So we've got 37 and then 98.6. And we've got 20 degrees, which is room temperature, which is 68 Fahrenheit. So that's room temp. I do this for myself, so to try to have a feeling of what Celsius. If you grew up using Celsius, then you don't need this, right? Obviously, but I do. And then we've got 0, which is 32. And then negative 273, which is absolute 0. What is that in Fahrenheit? I don't know. We could figure that out.
It's like -4. It's cold.
Is it?
It's really cold.
So that's coldest possible temperature.
You
273.
might want to wear a sweater. It's that cold.
Okay, so let's see. Oh, by the way, if we put some Kelvin on here, it's just going to be 273. Sorry, 373. And 273. The Kelvin degrees are exactly the same size as the Celsius degrees. You just shift the intercept. Whereas the Fahrenheit scale has a different slope. So the degrees are different sizes. All right, it's not just a different intercept. Okay, questions about any of this stuff? I don't know. Some people think that measurement is like the part of the drudgery of science, but I'm just fascinated by measurement. And I don't know why that is. I probably just sound weird, strange. But yeah.
How can we continue to use Fahrenheit if Celsius is, I guess you could say, better or more used?
I'm guessing it's the same reason we continue to use gallons and inches. And you know what's weird though is that like England, who came up with this thing, uses the SI system. So they were able to switch. I don't know, anybody from England?
But they still use
Tested
miles.
that?
They didn't switch to the euro.
I think they use miles. I was there this
Do they?
summer, and I think they use miles.
Yeah, they use
Really?
miles interchangeably, really.
Maybe it's just officially they've
I don't
switched to
think
the
they do
SI
that.
system. I don't know. It's not easy, and here's one reason. You have to retool factories, for one thing. So I don't know if you've ever had the frustration of trying to work with metric nuts with an English wrench, for example. So you have to retool things. So it's not just a matter of making some proclamation from on high, we're going to switch this. You're talking about, say, going into an automotive plant and changing all the machines. So it's not that simple. And I think that's part of the reason. But the fact that there are other countries who've done it kind of, it's a little suspicious. All right. So, but, the first measurements were like, counting. You don't think about counting as a measurement, but it is. Counting is a measurement. So maybe, and why is it, why do we have a base 10 system? Right? That's why we have a base 10 system. So Because you're sitting there, you're like, oh, that's 1 squirrel, that's 2 squirrels, that's 3 squirrels, that's 4 squirrels, that's 5 squirrels. But you're not even naming them 5. How many squirrels? You know? And then you can start doing like rudimentary math, you know? Like that. So that's measurement. We've gotten more sophisticated with it. But it's the same thing, basically. Okay. No questions. We're going to talk a little bit more about measurement. And my favorite topic of all, if you've had, well, my second favorite topic of all behind entropy is, well, third favorite topic? I don't know. It's right up there. Uncertainty. Family? Where's your family in all this, Dr. Green? Where do they rank? Oh, they're right up there. Okay, uncertainty in measurement. Now this is, I'm going to say one thing here that is challenging, but if you can really grasp it, it's going to help you a lot in your scientific career or your engineering career, and that is all measurements are inexact. Or no measurement is exact. I should put it that way. Every measurement has uncertainty. I don't care if the most sophisticated robot with a supercomputer brain made the measurement. It is not exact. Okay? I mean, you can take, and we have various balances in this room. We have some electronic balances. So here's an electronic balance. By the way, open up the cover before you try to measure on these, just so you know. We have a simple electronic balance. This one measures to the nearest 0.1 grams. So let's say I put an object on here, and this thing tells me it is 10.1 grams. That's what it reads out. 10.1 grams. Does that mean it's exactly 10.1? Well, it must be because a machine made the measurement, not some fallible, weak human. Right? Ah, take it over to the other balance we have, which has this glass case on the top of it. And this thing measures to the nearest 10,000th of a gram. So this thing, I put the same object on here, and it gives me 10.099. Well, that must be the true weight, the true mass. What do you think? No. No. It's like this. You can just keep going. You can keep stretching that thing out just like pi. So, no measurement is exact. It doesn't matter if it's a computer. As great as they are. They could be more precise than human, but that doesn't mean they're exact. There's some kind of an estimation process going on there. Think about a ruler. Well, actually, you know what? Let's do a little activity. So we got a little fun activity for us to do, and we won't finish this before. We won't finish this before the bell, but that's okay. We'll continue. All right, you know about the meniscus? The meniscus is the curved surface because the water has an attraction for glass, so it tries to climb up the sides. And so you get this kind of thing like this. And what you want to do is, now the other thing is it's not a clear line, it's more like this. What you want to do is read at the bottom of this, right there. That's how these instruments are calibrated, these volume measuring instruments. You want to read it that. And I won't tell you anything else. What I'm going to do is I'm going to pass each of these three around, and I want you to write down in your notes the volume that is contained, the volume of water in each one. It's not a test. Do not look at your neighbors. Have you ever heard of a social cascade? don't accept, it's what happens like if you're in a big group of people and somebody is the first one to vote, then there's a tendency for everyone else to vote with that first vote. Or if somebody gives an answer, it's a tendency for people to go along with that answer. So I don't want you to even show your answers to your neighbors. Cover them up. Keep them to yourself. This is for illustration purposes. So again, don't be worried if you think you're not exact. One thing I will warn you of though, this one has a scale that goes down and then it goes up. Make sure you measure it on the scale that goes down. So you know how many times scale goes down so you can measure how much you can spend. So yeah, just pass that around. And,